Thank you very much, and my thanks to the organizers for inviting me. It's the first time I am here in Arkansas, and I like it very much, I must say. So what I am going to talk about is some relations between Whitney problems and physics, both classical and quantum, which seem to me quite an interesting and unexpected. So let me start with repeating what is a Whitney problem. It was done several times already, but I need to repeat it. So something is given. What is given? A set E in Rn and a norm on a norm or semi-norm on a function space on Rn. What do we need to do? Compute the following quantity. Oh, one thing more. There is also a function on this subset, say real valued. We need to compute the following quantity, Fe norm, which is infimum of the norms of F capital, such that F capital restricted on E is F small. So it is a variational problem of this sort. Okay. What is known? Well, the Charlie's results are actually deal with the case when this norm is the CM norm x in Rn alpha less or equal than m, but the result is the following. This quantity, the infimum, is not computed. Actually, I think there is only one situation when this quantity is known, but this quantity is not computed. In this case, by the way, this infimum need not be a minimum. Therefore, we can add something else. If infimum is minimum, find a or the minimizer. It might be not unique. If not, if infimum is not a minimizer, find an almost minimizer. So in this case, this quantity was not computed, but Charlie has found, constructed, an almost minimizer. Okay, we have a minimizer, at least in this case, and there are also almost minimizers in case of Sobolev spaces. The question is, what do we do next after we have a minimizer? Well, a natural thing would be to try to compute the value of the minimizer, if it exists, or almost minimizer at different points. But this is not a very well posed problem, because especially almost minimizers, there are many of them, and they have different values at a given point. And therefore, it is not very clear what to try to find. But in the case when there is one minimizer, unique minimum, then this problem is very well posed and makes a lot of sense. Because, well, after all, when we extend the function f small to a function f capital, we usually need to compute some functionals of f capital, because it is exactly what why we were asked to do the extension. Okay. Let me suggest a very simple situation when the minimum is unique, when it can be explicitly computed, and it is, I think it is somewhat interesting in itself. Okay. Setup. Choose a weight function P of Xi and consider the following norm. Fp is integral over Rn f hat of Xi squared p squared of Xi d Xi. F hat is definitely the Fourier transform. And this is going to be the square of the norm. Well, such norms are quite useful. For example, if p of Xi, for example, is something like p squared of Xi, ak Xi to k from 0 to m, we get Sobolev norms. AK are positive numbers. And if p squared of Xi are of this form, Xi to k, mk squared, k from 0 to infinity, we get Danjois Carleman norms. So for this kind of norms, we can solve this problem exactly and very simply. We can compute all the quantities, and that's exactly what I want to say right now. But before we do this, let us assume that this set is finite, the number of points is n capital, and we have to assume something about p of Xi in order to be able to talk about the values of the function at a point. Let us assume that 1 over p squared of Xi is in L1 of Rn. In this case, delta x functionals are bounded in our norm P, in this one. It's easy. Okay. Now I want to formulate the following claim. C, what was the order? Fe. C of Fe norm P is explicitly computed, and I will give the formula. And the best possible extension, which with the minimal extension, is also explicitly computed. And I will do it in a moment. I need some additional considerations. Okay, let me do the following. Let me consider this function, take the inverse Fourier transform, and call it S. This function, I call it S. Okay, now let me consider the following matrix. Its entries are the following: S of x minus y, x and y in E. It is an n by n matrix, x minus y. Well, S is the Fourier transform of a positive function, so S, M sub E is positive definite. So M sub E in particular is invertible, exists. And the answer is going to be in terms of this S. First of all, this is nothing else but sum f of x m e minus 1 of xy, I better put it here, f of y, xy. This is the exact formula for this minimal possible norm, possible square of norm. It is the minimal possible square of norm. And if you wish, I can write a formula for the extension having this norm. It is the sum, what is it, s x minus y, m e minus 1 of y z, f of z, the sum over y and z in E. This gives you the extension with the best possible norm. Well, it is very easy to prove these results, nothing difficult at all, but they are part of a more general setting, which I am going to explain right now. And the setting is this. Let us consider norms, integral norms. Therefore, for example, maximum, supremum norms will not work in this setting. Let us consider the norm. And even in just a moment, in this situation, in the situation of infimum, we can easily, for example, raise this norm to some power. It is obvious that, well, the difference will be negligible. So, the norm of f would be, I'm sorry, instead of the norm of f, I will consider some quantity which I will call action functional, because this is its name in physics, which is integral of some function L depending upon f of x, f all derivatives of x, dx. And we integrate over Rn, all derivatives here. Okay, and actually what we are after the infimum of the A of f under the restriction that f restricted to E is f small. Okay? Well, we can get rid of this restriction with the help of Lagrange multipliers, and we can introduce a different action functional, which is L dx minus some lambda j f delta xj minus f of xj, and the sum is done over E, over A. And so we are interested in the absolute minimum of this functional, of this action functional, in the absolute minimum of this action functional. Well, we all know how to deal with this problem. And how do we deal with this problem? We write the Euler-Lagrange equation. And the opposite to what happens to the usual Euler-Lagrange equation, we have high derivatives. In physics, only the first derivatives are involved because of the causality principle, which requires that only the first derivatives are involved. But we are not, we do not care too much about causality, therefore we can easily involve higher derivatives, and recently I found a book in physics where they also consider higher order derivatives problems of this sort. And, well, we can write Euler-Lagrange equation, which is of the following sort. I will write it: sum minus d alpha. Okay. In df dl, I'm sorry, it is L. df alpha, I take the derivative dd alpha, equals the sum of lambda j delta x j. It is nothing else but the differential equation which describes the minimum of this function. So as we see from here, this is a nonlinear differential equation, and solution of this differential equation provide us the minimum if it exists. In our previous situation, in the situation that I have described here, in this situation, actually what we have this L being the sum of squares of derivatives with coefficients, sum of squares of derivatives. Why this was good? Because in this case, these derivatives gave us simply FA, and the differential equation proved to be a linear one. So there is nothing. That's why in this case we were able to get all formulas explicitly. Okay, so to some extent, if we want to consider this as a variational problem, well, there is not very much that one can do about this. This is more or less all. But as physics teaches us, it makes sense to switch from the Lagrangian formalism, from the variational problem in Lagrangian setting, to the Hamiltonian setting. And switching to the Hamiltonian setting, it does not give a lot of pluses in the classical situation of variational principle, but it gives a lot of pluses if we want to quantize the situation. So there was a famous saying by, I don't remember by whom, but someone very important in physics in the 19th century, where he said that the Hamiltonian formalism, though definitely very beautiful, gives almost nothing to professional physicists and gives almost nothing to engineers and very little to professional physicists. It was true until the procedure of quantization was invented in the 20s, and at this point it was found out that actually this is a very useful trick. The Hamiltonian formalism actually allows us to do a quantization much more effectively. Let me switch to this, and I want to explain some things about the relation between the usual Lagrangian formalism and usual Hamiltonian formalism, just to explain the reason why I got interested in that. So in the usual Hamiltonian formalism we have, well, there is one variable t only, and there is a function, well, let me have only one function, f of t. So we have the function of this sort, f of t and f prime of t. In the classical physics, this is the Lagrangian function, and this is the action functional. As you see, these two variables, f of t and f prime of t, are not independent. If you know one of them, f of t, you can compute the second of them. And this is a very important thing in all problems about Whitney, which are based on the fact that the derivatives of the function are not independent. New functions, they are dependent upon each other. They are very closely related to each other. What is the Hamiltonian formalism? It is actually a way to get rid of this interdependence of derivatives. That's how it goes. First, we switch from the Lagrange function to the Hamiltonian function. Let me, for simplicity, assume that t is not here. And I will have a function f of t, and another function p of t. Let me do it better. Q, p. It is supremum of p f prime minus L of Q of f prime. And just a moment, I will. Could you speak? Yes, usually, actually, all this works very well mathematically when the function L is convex. If it is not convex, there are a number of problems, and I don't want to address them. So let us, for now, assume that it is convex. It is called the Legendre transform. This is called the Legendre transform, and it works very nicely. You see, now for me, f prime is just another variable. I did not write f prime of t because t is irrelevant here. F prime is just another variable. And so we get a function of two new variables, q and p. And you can easily see that if Lagrangian function is the function on the tangent bundle, h is a function on the cotangent bundle because p is a functional. Okay. And then we plug in q is something here. Just a moment. Q is here. I'm sorry. I have changed the notation. Q is the first argument, simply the name of the first argument. Now I plug two absolutely unrelated functions, q of t and p of t, and consider the following q of t and p of t, and consider dt, and consider the following, which is q prime of t, p of t, dt. And consider the following expression. Actually, it is the same as Lagrangian, but written in terms of h. What is important is that Legendre transform is self-inverse. Its square is identity. It inverts itself. It is easy to see. Okay, so that's what we have. Well, then one can write the famous Lagrange equations, which q prime of t is dh dp, p prime of t is minus dh dq, or vice versa. I never remember. Let me say yes. Yes, that's right. And this couple of equations is equivalent to the Euler-Lagrange equations for this functional a of f. They're equivalent, simply equivalent. So something strange is happening here. Why something strange is happening here? In the Hamiltonian formalism, q of t and p of t are two completely independent functions. They are on absolutely equal footing. But after I solve this equation, after I solve this Hamiltonian equation, I get q and p, and p is the Legendre transform of the q prime. So somehow this system of differential equations returns us to functions q and q prime, which are closely related to each other. And the question is, what is the structure which returns us to this relation? The structure is definitely the so-called symplectic form, which is present on the cotangent bundle. And actually, these equations are written with the help of the symplectic form. But if you think about it a bit deeper, you will see that what is important not the symplectic form, but the Heisenberg-Weil group, which is closely connected to the symplectic form. Let me give you a definition of the Heisenberg-Weil group. It is simply, as I needed two n plus 1. Everything is true if q and p are not just one function, but a vector function. To n plus 1, n is the number of components in q. It is okay. And if I have two, so its points are q, p, and lambda. And actually I need not the group, but the related algebra. Q prime, p prime, lambda prime. By definition, it is the following object, 0, 0. And here is p of q prime minus p prime of q. It is the, I'm interested not in the Lie group, but in the Lie algebra. So I have to introduce the bracket here. Let me explain what is what. Q is from the so-called configuration space. P is an element of the dual space. So P of Q makes perfect sense. It is easy to check, actually very easy to check, that this formula produces a non-trivial Lie algebra. It is not a commutative Lie algebra, which is definitely the trivial one, but, well, the closest to the trivial Lie algebra. And, as a matter of fact, one can understand that the fact that the Hamiltonian system returns us to the function q and q prime is based on the structure of this Lie algebra. By the way, this Lie algebra actually it is the commutation relation, and one can easily see that the commutation relation mimics the commutation relation of multiplication by x and differentiation. And this is exactly why it returns differentiation to us. Now I need to go a bit further. How do we switch from classical mechanics to quantum mechanics? And I will explain this in terms of Feynman integrals, because it is to a very strong extent it is Feynman integrals in the Hamiltonian situation. It is a very deep idea, and I want to explain this. So we want to minimize A of, say, QP. Why? Because, well, this is the minimal principle of classical mechanics, which says that the trajectory a particle chooses is the trajectory which minimizes the action functional. But instead of that, we could do something different. Take e to the power I over h a of q p. Okay. Q and P are functions of T, and then integrate of the infinite dimensional space of functions of Q and P. This is called the Feynman integral. It has a lot of nice properties and one bad property. One bad property is that it doesn't exist. All other properties are nice. But nevertheless, though it does not exist, and there are strict mathematical results saying that it does not exist, physicists are using it for 60 years already, and in a lot of situations they get absolutely fantastic results, which can be verified in experiments up to, say, 26 digits in the answer. So there is absolutely no doubt in anyone's mind that this is a very meaningful formalism. It is a separate situation. One can make sense of all this, but this making sense is not that easy. One can make sense of all this. But why this is important? You see, h is the Planck constant, and Planck constant goes to 0. Immediately something strange appears. Constant is a constant is a constant, correct? It very rarely goes to 0. But the thing is that this is not a constant, but a constant with in some units. And if we use units of our everyday life, then this constant is very small. But if you use, say, units which are reasonable in the situation of, say, atomic particle physics, this is very close to 1. So the fact that h goes to 0 says nothing about this quantity. It says about the units we're choosing. Something about the units we're choosing. Okay. Now let us return to mathematics and look at this integral, imagining that it does exist. Imagine that it does exist. Correct? And tell me what happens to this integral as h goes to 0. If this integral does exist, then this integral is a standard integral of stationary phase method, isn't it? And stationary phase method says that it behaves asymptotically as some constants. I will not write them. I, h, a of q naught of t, p naught of t, q naught, p naught, q naught of t, p naught of t. Correct? Where q naught, p naught of t is exactly the function which delivers minimum to our action functional. So if I get h going to 0, that means I'm coming to our everyday units, then actually all this distribution of probabilities sits down on one trajectory, and this trajectory is the classical trajectory. Just a moment, I will go to that. Okay, now let me look at this expression, and this expression is the expression for the action functional. We have, as you see, integrate this functional with respect to p's and q's. Correct? And when we integrate this on e to the power of this with respect to p's, we see that this is going to be a Fourier transform. And Fourier transform will be computed at this point, q prime. And that's why this structure returns us to the derivative of the function q. You simply do it and you immediately see it. Now, what is the origin of this very important object? The origin is very interesting, and well, I will try to explain the origin of this expression, because it is really very interesting, but it is not that easy to get. So let me now see what will happen if we are considering, oops, I was supposed to say all this in the first 15 minutes. It seems as if I'm over time a little bit. Sorry. Let us see what will happen if we are try to do the higher derivatives formalism, Hamiltonian formalism. Okay, actually nothing very bad is happening. So, imagine, and there are many variables, not one variable, but many variables. So I have function f, and I have its derivatives, say lesser or equal than m. Okay? So what is the derivative of the function? It is a function which goes, I'm sorry, no, it is not omega, it is from Rn to the space of symmetric, I'm sorry, I will put here k, symmetric k forms on Rn, because fk is nothing, at of x is nothing but f, the string of f alpha of x, alpha equals k. So it is better to treat fk as a function of x with values in symmetric k-linear forms. Symmetric k-linear forms. Okay. So I take the direct sum of symmetric k-linear forms on Rn, k from 0 to m, and therefore I can consider Jf, the jet of f, as a function from Rn with values in this space. Definitely not all functions with values in this set are derivatives. There must be conditions, which we all know, but nevertheless it is here. It is well known that symmetric forms on Rn are dual to the symmetrized tensor product, symmetrized tensor power of k. And therefore, this is dual to the following space Rn tensor k, not tensor, but symmetrized tensor k, k from 0 to m, and dual. And this space is a very usual physical space. It is called the Fock space, finite dimensional Fock space. Okay. Now I want to introduce the related, actually to mimic this, what is called, the Legendre transform. So if I have a function, some function, say L of f alpha, I do the following. I take jf and jf and put not here, and I will explain this jf, k here, minus, and take supremum over j naught f. Let me explain what j naught f. Jf is the set of all, it is the function, and together with all its derivatives. J naught means that I disregard the zero derivative, the function itself. So I better write this as j naught f. So f is a separate variable. And let us call it Hamiltonian. It is going to be the function of k, and definitely of f. F remains the function of k and f. Okay. Then we can, actually we can easily repeat the usual Hamiltonian formalism and get the Hamiltonian system. It is not a big deal, but it is not what I want to do. I want to quantize this Hamiltonian. I want to quantize this Hamiltonian. That means I want to write something like this expression and take exponent of this expression. But now I need to understand what is this. And now I will try to explain what is this term. Okay, that's how it works. Okay, that's how it works. You take the function of h of f and k. I have just introduced it. It is introduced with the help of the Legendre transform. Do the Fourier transform with respect to k, the usual Fourier transform. And you will get a bit different, you will get a Lagrangian, but a bit different Lagrangian, which depends upon f. It is only with respect to k. F is not here. And here I will have g naught of some not f, something else, g. I will get here. Now, this is a function on, the function of the following, on the following set. It is the function on symmetric k Rn on this linear set. But this linear set carries a natural structure of a Lie algebra. Let me explain. So if I have, let me take the element of this set. So what does it consist of? Let me use again. It consists of Q, the 0, consists of, say, F1, it is linear form, F2, it is bilinear form, symmetric, Fm, correct? And I want to get its bracket with Q prime, F1 prime, which primes simply denote different elements of the same space. That's what I get. 0 on the first place. Then I must get a linear form. How do I get a linear form? I get it this way. F2 of Q prime minus F2 prime of Q. F2 is a bilinear form. I plug one element from the other factor to it, and there is one guy left. Correct? As a matter of fact, I'm very sorry. I have to start with F1 of Q minus F1 prime of Q prime. It will be a number.
Are Q and Q prime simply numbers?
Simply numbers. Simply numbers.
Then what is F1 of Q?
Not numbers, vectors.
Ah, okay.
They're vectors. I'm sorry. Okay, so F1 of Q is F1 of Q prime and no prime here. Then I am doing F2 of Q prime minus F2 prime of Q, and so on. Here I get simply a number. Okay. I'm very sorry. I'm trying to be very fast in this case. So a better way, it will be F0 and F0 prime here. One place more. So the place which is occupied by Q is, we get 0 here. The place which is occupied by this is F0 is a number, 0 form. It is F1 of Q prime minus F1 prime of Q. F2 of Q prime minus F2 prime of Q, and so on. One can easily check that it is a nilpotent Lie algebra. It is easy to check, and this is what we need. Now, if we have a Lie algebra, then we can consider its enveloping algebra. So Lie algebra can be embedded into an associative algebra, so that the commutator in this associative algebra becomes the bracket in the Lie algebra. It is a general situation. So what we need to do is to take this function, it is a function, okay, and do the following. This is J naught of G. I must do the following. I must turn it into a distribution, which is supported at the origin. Let me explain how I do this. So if I have a number, I simply take the number and multiply by delta function at the origin. It will be okay. If I have a vector, I will consider the derivative of delta function along this vector at the origin. If I have a bilinear form, I will consider the second derivative of this, the second derivative of the delta functional at this point in the direction of this as a bilinear form, and so on. Is it clear or not very much?
I'm wondering whether you really want the bilinear form or whether you want a tensor product of vectors.
Yes, definitely I want tensor product of vectors. Okay, let me put it this way. Okay, if I have a bilinear form, I can make, if I have a bilinear form, I can represent it as the sum of tensor products. Yes, if I have a sum of tensor products, I can take delta, the derivative of delta function at 0 in the direction of these elements of the tensor product and take the sum. It will be a delta, it will be a distribution supported at the origin. Then, if so, I will switch from this function to a delta measure supported at the origin. Now I will take the convolution exponent of this delta measure. So I take the convolution of this delta, delta distribution with itself, plus convolute it with itself and itself once more, divide by 3 factorial, and all that stuff. Okay. This may actually, this is very closely related. This is not closely related, but it is the same as the enveloping multiplication then enveloping algebra. So in multiplication then enveloping algebra is obtained exactly this way. You first turn an element of the Lie algebra into a functional, into a functional on the supported at the origin, and then you do the convolutions. Okay, so we can get the exponent either this way of this guy. We can get the exponent. And one can prove that it can be, I put I in front. One can prove that it can be written as e to the power I, the function. Then there will be some kind of measure, which I don't want to write down, but this kind of measure will be exactly this expression that I have pointed to earlier. This expression, its origin is exactly what I said. So, taking actually this is called the partition function of this system, and all quantities we want to compute are derivatives of this partition function, and they will be in terms of this measure, they will be exactly what you expect, the expected values of the quantities you are interested in. Okay, so unfortunately I do not have. Oops, I'm over my time already. I did not have time to explain many things here, and I was in a rush, so I'm very sorry about that. Thank you very much.
So this is incidental to your main point, but it was striking for those of us who don't know much physics. You said that the Lagrangian should not involve higher derivatives of the fields because we want causality.
Yes.
Why, if you include higher derivatives of the fields in the Lagrangian, do you violate causality?
Well, let me explain it not in the case of the field, but in the case of quantum mechanics, not field theory, but mechanics. The causality means that if you know the position and the velocity at one moment, you must know everything. That means you are only allowed to use first derivatives. But as for fields, I do not know any Well, it is simply being extended by analogy. But I have not seen a single situation where you have high derivatives.
In general relativity, isn't the Lagrangian the...
Second, yes. They also include second derivatives. It is quite possible, yes. But it does not include second derivatives in the kinetic term. It does not include, yes. Because kinetic terms is what where causality really appears. Thank you.